So yeah, good afternoon again. Is my
Good
screen visible?
afternoon, ma'am.
Yeah, good afternoon. Is my screen visible?
Yes, ma'am.
Okay. Yeah. So your quiz 2 is over and now we will start with the week 9, right? So today is a week 9 summary session. What is the syllabus for end term exam? It's from week 1 to week 12. Yes, it's week 1 to 12. So yeah, in week 9, we'll be basically seeing about time quantization, amplitude quantization, then sample and hold circuit, then flash ADC, then capacitor based some circuits. We will be seeing like capacitive mixers and switch capacitors. So have you guys watched the week 9 lectures?
Yes, ma'am.
Okay, good. Why do we need to do this time quantization and amplitude quantization?
To convert the continuous values into discrete values.
Yes, right. We are converting continuous values into discrete values. And why are we converting it into some discrete values? Because usually computers cannot store analog signals, right?
Yes, ma'am.
In real time, the signals, it will be varying with respect to time. If it is a signal, this time can be 1 second, but this analog signal will also be holding true for 1.1 second or 1.01 second or 1.001 second. The analog signal contains a value, let it be v of t. For each and every second, there will be a value of v of t. So the time is actually has infinite values, right? In the same way, at one point, if it is in the range of 1 to 2, it can be 1.7823 and it can be going on. This can also be represented using infinite values. So, analog signals in nature are infinite, right? Infinite in x-axis and in y-axis also, right? So, this infinite nature of this analog signals cannot be read or stored in a computer. That's why we are going to discretize it first, then we will digitalize it next, right? Yeah. So let me take a sine signal. It is with respect to t, time axis, and v of t. This is an analog signal, right? So what I'm going to do is I'm going to break this time axis into certain samples. So let it be this value be 1 second. So from 0 to 1 second, that value I'm going to break it into certain parts, and each part I'm going to give some value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So converting this 0 to 1 second into this 0 to 10 values, what it is called? It is for time quantization, right?
Yes, ma'am.
Yes. In the same way, I will also be breaking this y-axis. Again to 1, 2, 3, 4, 5, 6, 7, 8. And this process, let it be like from
Okay.
0 volts to 5 volts. Again, the 0 to 5 volts, I am going to write in terms of 0 to 10. And this I will call it as
Amplitude
amplitude
quantization.
quantization. Yes. So why am I making in terms of an integers? Because basically our computers are there, no? It can read only values zeros and ones, right? And these integer values, we can convert it into zeros and one by terms of binary conversion. There are ways, right? So that's why whatever analog signal I am having, first I am discretizing it into some points in x-axis and y-axis so that I'll get some integer value. Then that integer value, I can convert it into zeros and ones. And this process of converting these integer values into zeros and ones, right? You will learn it in your next week 10 lectures. So it's all about binary conversion and all. Is it fine? Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now, what is sampling frequency? If I say sampling frequency is 4 hertz, then I am giving this sine signal which is under 0 to 1 second. So what I'm doing, how many samples am I going to collect from this signal? My sampling frequency is 4 hertz and my signal duration is 0 to 1 second. How many samples will I get?
4.
Yeah. What is the formula for number of samples? It is sampling rate into time of capture, right? If my time of capture is from 0 to 1 second and my sampling rate is 4 hertz, 4 hertz is nothing but 4 samples I'm collecting per second into 1 second. The second and second will get cancelled. So basically 4 samples I will get. So it is basically collecting these 4 equally divided samples at 0.5 seconds, 0.25 seconds and 0.75 seconds, right? And now if you see my x-axis, it is 0, 0 0.25, 0 0.5, 0 0.75 and 1 second. So there are 4 samples I am collecting at this 4 points, right? And I will be representing this as 1, 2, 3, 4. Here it is time, whereas here it is the number of samples. If my signal is a slow moving, if my signal is slowly changing with respect to time, and I have another one signal which is changing rapidly with respect to time, right? Here if I'm assuming my sampling frequency is some value x, then let it be fs1. If this is fs2, this is the sampling frequency for this wave. Should it be like, should it increase with should it increase or it should be lower? Should it be higher or lower? If a wave is changing slowly, I am having a small sampling frequency, right? If my input is like changing rapidly, should I choose a sampling frequency which should be higher or should it be lower?
Higher.
Yeah. If a signal is fast changing signal, you should choose a sampling frequency which is higher, because if it is the same waveform 1 second, if I'm choosing the same 4 hertz, I'll be getting this point, this point, this point, and this point, right? So if I reconstruct with the same value, it will be just a straight line. I will not be able to reconstruct at my original signal. That's why if my signal is changing fastly, my sampling frequency should also be higher. I should choose in such a way that my that my sampling rate is able to capture all the changes that is happening in my input signal, right? Yeah. The next one is amplitude quantization. Do you guys have any doubt in time quantization?
No, ma'am.
Okay. So yeah, next we'll go to amplitude quantization. So here we saw that we have break down the x-axis, that is the time axis, into 4 points, and in each of these points, x of 0, x of 1, x of 2, x of 3, each value can be represented by a value which is infinite in nature. So I have to find a way to discretize this also. So that's why I'm going for amplitude quantization. Here, what is delta? Do you guys know this formula? Delta is equal to range by m.
Delta is the step voltage.
Yes. Step voltage. What is m?
Levels.
Yes. It's a level. And range is the range of the input that I am feeding. Let me say my input is in the range of 2 volts to 4 volts. Okay. And I'm going to discretize in 2 more levels. So my total level is 0, 1, 2. Okay, totally 4. First level, second level, third level, and 4 level. So my m is 4. My range is, what is my range here? It's 4 volt minus 2 volt, right? My range
Yes,
is
ma'am.
the range of the input value. So it is 2 volts. What is the delta value here?
0.5.
Yeah.
0.5.
Yeah. So what is this value? The point which
It's
I'm showing.
2.5.
Yeah, it's 2.5 volt.
Then 3.
That will be on 3 volt, 3.5 volt,
3.5.
right?
Then 4. Yes, ma'am.
So then again, I'll be marking this as 0, 1, 2, 3, 4, right? And my time axis is also in 1, 2, 3, 4. So now I have discretized my time axis and my amplitude axis also, right?
Yes, ma'am.
Yes, ma'am.
And we have come across what are the important formulas in time sampling and here which we will be using for our problems. Number of samples is equal to sampling rate into time of capture, right? And another one is what is TS? It is the duration between two successive samples, right? What is the formula for TS? If TS is the duration between two successive samples, TS is equal to 1 by Fs, right?
Yes, ma'am.
Yes, ma'am.
In the same way, for amplitude quantization, we have delta is equal to range by level.
And
Yes. So basically, initially we had a continuous signal, continuous analog signal that I first quantized with respect to time. So I got x of n ts. Again, I'm quantizing the amplitude. So I'll get xq of nts. So this is what we are done till now. So what is sample and hold circuit? What does it contain? If there is a DC voltage, there will be a switch, right? And then a capacitance connected in series. And we will also see about the characteristics of this switch. What happens if the switch is on?
no current will be flow.
If the switch is on, well, no current will be flowing.
Yes,
Current will
ma'am.
be flowing, right? If the switch is on, it means it is closed. So all the current will be flowing, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
So when switch is on, resistance is equal to 0 for all current. In the same way, if the switch is off is means the switch is open circuited. The resistance will be infinity, whatever the voltage is, right? So
Yes.
Yes, ma'am.
my VA characteristics will be is this for on state or off state? For all, this is for on state, right?
Yes, ma'am.
And this is for off state. Because while the switch is on, the current will be flowing. If the switch is off, the current will be 0. And voltage can be varying. So this is the VA characteristics of the switch. Then what else we saw in this week? We will see about the flash ADC. What is ADC? It's analog to digital converter, right?
Yes, ma'am.
Yeah. So this is the simple analog to digital converter. It has 4 levels. Yeah, it has 4 resistors. So there is a X max. I'm taking this X max as a voltage value, and I'm going to consider 3 levels. So what is this value? How to find this value? I'm assuming this all the resistance are R, that is same. So what is the voltage across this point? Okay, I'll give X max as some value so that it will be easier. 4 volts. How to find the, let me take it as V1, V2, V3. What is the value of V1?
4 upon 3.
We can use the voltage divider, right? Here it is 0 volts.
Yes, ma'am.
If I'm going to find the voltage across this point, so it is basically 3R by total resistance is 4R into the X max, which is 4 volts, right? So R will get cancelled, 4 will be cancelled. So V1 is 3 volts. In the same way, what is V2? Tell the formula how to find V2. We know, right? If there is a, this is the formula for voltage divider, right? If it is R1, R2, and here I am having a V input value. Let me take it as V out here. V out is equal to R2 by sum of R1 plus R2 into V in. Right? So in the same way, if I'm going to find the voltage at this point, I will add all the resistors that are coming after that. So R, all this R, so 3R divided by the total resistance 4R into the total voltage, input voltage, that is 4 volts. So it is 3 volts. So now tell me what is V2? How to find V2?
2R upon 4R into 4V.
Yes. So it's 2 volts. So again, this will be 1R by total resistance 4R into 4 volts is equal to 1 volts, right?
Yes, ma'am.
And this one is 0 volts. Now, I'm going to give this voltage to a amplifier, to the negative terminal of the amplifier. And for flash ADC, I will choose an amplifier such that the gain should be very high, right? So that my output will either be plus VDD or minus VDD. See, if my amplifier is so high, so I said I'm selecting my amplification is 100 and or 10 is fine. I'm powering the supply using 4 plus 4 volts and minus 4 volts. And so, somehow I'm giving an input 2 volts here. So after amplification, my input will become 20 volts, right? But due to this power supply, I will not get 20 volts. Rather, I will be getting some value which is maximum. Like I will get it around 3.5 volts or some fixed value I will get, which is a saturated value, right? So I will get plus VDD. One saturated value I will get. Either I might get 4 also, depending on the internal resistance present within the amplifier, right?
Yes, ma'am.
And
Yes,
also
ma'am.
this is a differential amplifier. Plus and minus. So that is this value here. Again, I will have one value here. Let it be 1 volt or okay. If the input is 1 volt, I'm giving. So basically, the difference will be amplified. It is minus 2. Minus 2 will be, I'll be getting one value depending on that. So that is the characteristics of this amplifier. Now, this is my input, which I
Ma'am,
will,
can you explain one
yes,
time again differential amplifier?
okay. So there is an amplifier. There is a positive terminal and negative terminal, right?
Yes, ma'am.
So, okay. While seeing non-inverting amplifier, where did we give the input? We gave it in the positive terminal, right?
Yes, ma'am.
Whereas this is the non-inverting one. Whereas this one is the inverting one, right?
Yes, ma'am.
In non-inverting amplifier, the output voltage will be the amplified version of the input voltage. And this will be positive. Vout will be positive, right? Whereas in the input inverting amplifier, my output is the negative A of Vin. Now, what I'm doing is, in the differential amplifier, I am giving a value for Vin1 for the positive terminal and Vin2 to the negative terminal. And I'm getting a V output, which is amplified. The Vin which is fed to the positive will be Vin plus 1, whereas negative terminal will become minus Vin2, right? So my
Yes, ma'am.
output
We
is
pass delta with it.
yeah, the difference between the two signal has been amplified, right? That is a differential amplifier.
Okay, ma'am. Got it. Thank you.
Yeah. Now as in the lecture, we'll give the same value 2.75 volt. If I am feeding the input here, I am giving in the positive, right? Yeah. Here I will get, here I am comparing 1 volt and 2.75 volt. So the difference is 1.75 volt, and that 1.75 volt will be amplified, right? It will be amplified in many times such that the positive saturation is reached. So output I'll get plus VDD, right? Are you understanding how we are getting plus VDD here? Here I am feeding 1 volt to this amplifier, whereas here 2.75 is coming. This will amplify, first it will take the difference. It is 1.75. And this 1.75 is positive value. It is amplified by manifold so that this saturation will be the output plus VDD. In the same way, 2 volts and 2.75 will be compared. I will get the difference is 0.75, which is a positive value. So again, I'll get plus VDD, right?
Plus VDD. Yes, ma'am.
Yeah. In the first amplifier here, my positive terminal value is 2.75, whereas my negative terminal value is 3 volt. So here, my negative value will be amplified, right? So
Yes.
So
here,
here you will get
the
minus
output is
VDD.
minus VDD. Yes. In the same way, here, in this differential amplifier, if I am supplying this with 4 volt and if I am supplying this with 0 volt, my plus VDD will become 4 volts, right? And my minus VDD will become 0 volts. So this minus VDD will actually become 0 and plus VDD will become 4 and 4, right? Is it clear?
Yes, ma'am.
Yes, ma'am.
So whatever values I am getting, I will add and then I will get a value. Here I will be getting 8, right? And depending on this value and mapping to the initial value, I will be getting some discrete value, right? XQ of NTS. So basically I'm getting an integer value here. Is it clear? This is the principle of flash ADC. For now, you just understand how the flash ADC is operating. And when we see little more examples related to working and like problems, you will be completely able to understand the flash ADC. For now, you just understand there are many amplifiers in the circuit. Then to each amplifier in the negative terminal, we are feeding the fixed voltage values, which are considered as the levels. Then in the positive terminal, we'll feed the input, and then the output will be some plus VDD value or minus VDD value. Either I can map it directly, or this 4 I can make if I can assume like whenever 4 comes, I will take it as 1 and then I will feed it to the addition circuit. In the same way, if you notice, here there are only 3 levels, right? Here I can also have 8 levels. Let it be 8 volt, 7 volt, 6 volt, 5 volt, 4 volt, 3 volt, 2 volt, 1 volt, and ground. And if I'm feeding an input as 5.6 volts, how many plus VDD will I get and how many zeros will I get? Tell me the number of plus VDDs I will get and the number of zeros I will get.
Five plus BTDT and
Yes.
2 zeros.
Yeah, for 5.6 volts. If I'm feeding
Yes.
3.2 volts, how many plus VDDs and zeros will I get?
3 VDT plus VDT and 4
Yeah,
zeros.
4 zeros. If I'm feeding 6.8 volts, what will I get?
6 plus VDT and 1 0.
Yeah. So basically, I'm able to find the voltage, right? By counting the number of plus VDD, I'm able to find the values. Is it clear now? What is that summing
Yes,
doing?
ma'am.
Yeah. So basically, by knowing the how much number of plus VDDs and number of zeros you are getting, we can actually map it to the value and we can take a guess. Oh, this is the value that has been fed to that circuit like that. I hope it is clear now.
Yes, ma'am.
Okay.
Ma'am, but if we subtract from 5 minus 5.6, it gets negative. So the plus VDD is 4 and 0 is 3.
I'm actually feeding this 5 volts to the negative terminal, right? 5.6 will be fed to the positive terminal. So 5.6 minus 5. That's how we did here, right? See, the input is fed to the positive terminal and this voltage divider circuit is fed to the negative terminal. Is it out clear?
Yes,
Or
ma'am.
okay. So basically, flash ADC is a
Ma'am, where
simplest.
we are using this flash is ADC.
Flash ADC. See, normally nowadays flash ADCs are not very common because see, if I am here, I am just having only. See, let me take this one. Here there are only 8 levels, right? For 8 levels, I need 1, 2, 3. Okay, 1, 2, 3, 4, 5, 6, 7, 8 resistors and around 8 to 9 amplifiers also, right? 7 amplifiers I have
Yeah.
to find. And this flash ADC will be able to measure only 1 volt, 2 volt, 3 volt, like whatever values. If you give, even if you give 4.2 volts or 4.4 volts or 4.6 volts, it will be mapped to 4 volts, right? So many information in between are lost. So if you want, what if I want to, like, if I want 16 levels, but I want to measure between 0 to 8 volts, what should I do? I should increase the number of resistors, right? And amplifiers. Are you able to understand? I am just going to increase the level like this. If I increase the level, 7.5 volt, 6.5 volt, 5.5 volt, such that there is a resistor in each of this. This is the only way where I can modify the given circuit to measure 1 to 1.5 to 2.5, right? Okay, wait, I think I'm a little bit. Initially, I had this circuit, right? Where I gave 8 volts, so that 7 volts, 6 volts, 5 volts was given. So even if I find 6.2 volts, 6.4 volts or 6.6 volts, all will read as 6 volts. If I am doubling the number of resistors I am using, like here it is 7 volt, here it is 7.5 volt, here it is 6 volts, here it is 6.5 volts, here it is 5 volts, 5.5 volts and 5 volts, right? And again, like if I am using in place of 3 resistors, I am using here 6 resistors, right? So that I can calculate one more level, right? So if I give 6.2 volts to this circuit, what will my flash ADC give? How will it detect it as? Is it confusing? So what I'm saying is, see, in first case, there is a 8 volt I'm giving as input. There I used 8 resistors. So I use 7 resistors and 8 amplifiers to get this combination, right? Where I can detect this around 8 steps, 7 volts, 6 volts, 5 volts, 3 volts, 4 volts, 3 volts, like that I can detect. If I am doubling the resistor, number of resistors I have used, and I am increasing the number of amplifiers I am using. Are you guys able to understand what I'm trying to say? Or is it confusing?
Yes, ma'am.
Yeah. If I am doubling it, so that I can measure not only 1, 2, but I'll be able to measure 1, 1.5, 2, 2.5. Like here delta is 1, whereas in this circuit delta is 0.5, right?
0.5. Yes, ma'am.
Yeah. So here 6.2 will be mapped as 6 volts. 6.4 will also be mapped as 6 volts.
6 volts.
6.6 will be mapped as 6.5 volts.
6.5.
So here, in order to measure the intermediate values, we are actually doubling the number of resistors and doubling the number of amplifiers we are using. So if I want to measure 0.2 microvolts, this is 5 volts, here it is 1 volt. If I want a delta value such that it is 0.2 microvolts, imagine the number of number of resistors and amplifiers that I have to use. It will be going in some
Yes, ma'am. It will be
yeah,
Yes.
thousands.
very high. Yeah, it will be in thousands. So that's the reason we don't go for flash ADC when you want like want to measure this microvolts and all. So if I want is there any other way I can reduce the delta value here instead of increasing this number of resistors and number of amplifiers, which is the other case where my delta value will increase? What else should I change?
Capacitor value.
No, it's this
Sorry, the
Vmax
distance
value.
value.
No, this Vmax value. If it is 8 volts, then this will become, see, if it is 8 volts here, it is 7 volts, 6 volts, 5 volts. What if it is 4 volts? What I'm saying is, wait. Here it is 8 volts, 7 volts, 6 volts, 5 volts, 4 volts, 3 volts, 2 volts, 1 volt, and here it is 0 volts, right? Here, first case is Vmax is equal to 8 volts. And I'm in all the flash ADC, all the resistors, we are choosing it to be the same value, right? So for Vmax is equal to 8 volts, delta is equal to, what is the delta value? 1 volts, right?
Yes, ma'am.
Yes,
If I
ma'am.
am changing this Vmax as 4 volts, what is my new delta value? And what is my new step value?
0.5.
Yeah, it's 0.5 value, right? So basically, this one, it will not be 1 volt, it will be 0.5 volt, 1 volt, 1.5 volt, 2 volt, 2.5 volt, 3 volt, 3.5 volt, then that is 4 volts. Again, what if my Vmax is 2 volts? What will my delta new value again?
0.25.
Yeah, it's 0.25, right? So again, my delta nu is decreasing, right? It will be 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75. So what does it say? If my Vmax is decreasing, my delta, that is the stepping voltage, will increase. It will also decrease. That means I will be able to measure even a small change in the voltage levels, right?
Yes, ma'am.
Yeah. So there are two ways. Either I have to reduce Vmax, otherwise I have to increase the number of resistors and amplifiers I'm using to measure the smallest changes. So flash ADC is useful only when you want to learn how a ADC is working. For the first time, if you are hearing ADC, flash ADC will help you understand how it is working, its basics and all. But nowadays, in whatever ADC they are using, they don't use flash ADC because it is bulky. Whenever we need a small, want to measure the smallest change. So basically, now we go for other ADCs like counter ADC, then sigma delta ADC, and there are many other types of ADC which we will be studying in future courses like EEC or analog electronics. In that, you will be learning this. Okay. Then so yeah, then we will solve a few problems. Then we will again go to the lecture. So this is the first question of practice assignment. How many samples are obtained if an input audio signal of duration 10 seconds is sampled at the following rate, 8 kilohertz? So what are they asking? They are asking the number of samples, right? And they are given the sampling rate. So how to find the number of samples? Hello, am I audible?
It's sampling rate multiplied by the time. Second.
Yeah.
Multiplied by 10 seconds.
So number of samples is nothing but sampling rate into capture time,
Time
right?
capture time. Yes, ma'am.
Is sampling rate is 8K, whereas capture time is 10 seconds. So it is 80K. So I'll get 80K samples. So again, the next question is, they are given the total number of samples. The number of samples is 352800 and sampling rate they are given, and they asked us to find the duration of the input signal, that is the T capture. How to find? What's the formula? From the same formula, right?
We'll just,
Number of samples
yes, ma'am. We'll just divide the
divided
sample
by
by
Fs.
sample frequency.
Yeah. Then you'll get the answer. Then consider the amplitude quantization of 128 levels for the voltage range of 1 volt to 5 volt. So they are given the range 1 to 5 volt. That is 5 minus 1 is equal to 4 volt. And M they are given. M is equal to 128 levels. And they have asked us to find the magnitude of each voltage step. That is the delta value. So what is the delta value?
It's 4 divided by 128.
Yeah.
0.03.
Is it 0.0?
31. 0.031.
Yeah, it's 0.032.
0.033125.
Okay. Is it clear? Do anyone have any doubt till now?
No, ma'am.
No, ma'am.
So yeah. Now we will go to the next part, which is capacitor based circuits. We will be seeing about charge sharing. If this is VDC and there is a switch here, So there are 2 switches and 2 capacitors. And now phi 1 is the control of switch 1 and phi 2 is the control of switch 2. Initially, till time t1, phi 1 is on. From t2 to t3, phi 2 is on, right? So this is the condition for the switch. So we will find from 0 to t1. For time 0 to t1, my circuit will be S1 will be closed and S2 will be open. So it will be like this, right? VDC C1. And assuming this T1 is a large time such that the voltage across the capacitor will actually become
VDC.
VDC. Yes. From time T1 to T2. That is from this time to this time where both the switches are open, right? Only C1 is standing alone, C2 is standing alone. What is the voltage that is stored in this capacitor C1?
VDC.
It's VDC.
VDC.
Whereas in C2, the stored capacitor is 0. Yeah. Now, from time T2 to T3, switch S1 is open and switch S2 is closed, right? Voltage across capacitor C1 at time T2 is VDC. Whereas voltage across the capacitor C2 at time T2 is equal to 0, right? That is the initial
Yes.
capacitance now. But if we connect over the time T2 to T3, what will be the voltage across the capacitor C2? Will it be VDC?
No, ma'am.
No, ma'am.
Yeah. Because only when we connect a capacitor across a battery or voltage source, then only the voltage will be the same as the voltage DC source. Because it has infinite charges, right? Whereas when we
Yes,
are
ma'am.
connecting two capacitance, here the charge is conserved. So the charge present in the capacitor is limited. So initially, charge across C1, I will take it as Q1, and charge across C2, I will take it as Q2. Q1 is equal to C1 VDC.
VDC.
Yeah. The charge in Q2 is equal to 0
0.
since the voltage is 0. Then at the final, after at the time T3, after many times, what will happen is, since this capacitor C1 and C2 are connected in parallel, the voltage will be same, right? The voltage across C1 will also be equal to the voltage across C2. So Q1 will be C1 V, a common V final. Q2 is equal to C2 V final, right? Are you able to understand why we are writing as C1 VF
Yes,
and
ma'am.
C2 VF? Because the voltage across the two capacitors will be same because they are connected in parallel. Yeah. Now, Q total at initial will be equal to Q total in final because the charge is conserved in the circuit. So it is C1 VDC is equal to C1 VF plus C2 VF. My final voltage is equal to C1 by C1 plus C2 into VDC, right? This is the voltage across both the capacitors. Now,
Excuse me, ma'am.
yes,
I'm getting this
which one?
previous
This whole,
which no
the whole,
that
how?
yes
Hello, your voice is-
from time T0 to T1 the value the voltage across the C1 and C2 That one.
Okay. See, this is the timestamp, okay? This is how the switch work. From 0 to T1, S1 is closed, S2 is open. Then from T1 to T2, both the switches are open. Then from T2 to T3, only the switch S2 is closed, right? This is the condition. So I'm going to break it into three conditions. So one is from 0 to T1, then from T1 to T2, then from T2 to T3, okay? From 0 to T1, only my switch S1 is closed and my switch S2 is open. So basically, this switch is open, so current will not be flowing. So I'm not considering that part. I'm considering only VDC and C1. So from initially, okay, voltage across the capacitor C1 at 0. What is the voltage across this capacitor at 0th time? A voltage source VDCE is connected in series with a capacitor C1. Okay. At 0th time, what is the voltage across the capacitance C1? It's 0, right? Then over time, this voltage will charge this capacitance, like it will be sending the charges. Plus, 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 minus, minus, minus. Then there will be some potential difference which will be developed. Since they both are in parallel, after a long time, the voltage across this capacitance will actually become VDC. Right? Are you clear with this?
Yes, ma'am.
Yeah. Then at time T1 to T2, that is now my switch S1 is open. So this switch one is also open. Then this switch is also open. So there is one capacitance C1, C2 is also there, but it is not connected with anything. So this capacitance is charged now. Now it can't discharge. So the VDC is retained in the capacitance C1, whereas in C2, the initial capacitance is again 0, right? Maybe this I can take it as T1.
Yes, ma'am.
Yeah. Now T2 to T3. The voltage across the capacitance C1 is still VDC, right? At T2, that is initially. Now T2 is the initial condition, right? Voltage across C1 at T2 is again VDC. Whereas here at time T2 is 0, right? So I can write it as, this is from at time T2. Here it is VDC C1 ground. C2, the voltage is initially 0. Okay. So this is how it is. Okay. Is it clear?
Yes, ma'am.
Now, if I am connecting a battery source across a capacitor, and if this VDC is 5 volt, after a long time, this capacitor will also get 5 volt. Because this voltage source will have infinite charges. So it will be feeding charge and then such that it will reach 5 volts. Whereas when I am connecting two capacitor, it will not happen like that because here there is only a limited amount of charges and that charge has to feed this capacitor and here the voltage has to rise. But the voltage rises in such a way that the voltage across this capacitor C1 and this capacitor C2 will be same because C1 and C2 are connected in parallel. Always in a parallel connection, the voltage will be same, right? This voltage will be same and this voltage will be same, right?
Yes,
We know
ma'am.
that, right? Yeah. So we know that so this is initially at time T2. What is the charge? So the charge stored by C1 is Q1 and charge stored by C2 is Q2. Q is equal to CV. So Q1 is equal to C1 VDC. Q2 is equal to C2 into 0. So it is 0. Okay. Now at time T3. At time T3, this VDC is also changed to V final. And this 0 volts will also be changing to V final. Why? Because from T2 to T3, the charge movement will take place, and charge will be moving in such a way that C1 and C2 will be having the same voltage Vf, because they both are connected in parallel, right? So Q1 will be C1 V final and Q2 will be C2 V final. And in this, total charge is equal to C1 VDC plus 0. At time T3, this total charge is equal to C1 VF plus C2 VF. And you see in this closed circuit, the charge is like circulating. The charge will not be lost. That is what we call it as conservation of charge. That means the charge is not going out of the circuit. It is like circulating within the circuit. That's why initially the charge I'm having, no, that is equal to the charge that it is found at the final. So that's why Qt initial is equal to Qt final. So C1 VDC is equal to C1 VF plus C2 VF. Now from this we can find Vf, which is equal to C1 by C1 plus C2 into VDC. So we have finally reached the value of Vf. Vf is nothing but the voltage across C1 and it is also the voltage across C2. We have found it in terms of VDC. Is it clear now?
Yeah, now thank you, ma'am.
Yeah. Now again. Now we will see another case where there is a voltage source here. Let it be V1 and there is a switch S1. There is a capacitor C1, switch S2, then again capacitor, switch S3, then again a voltage source V2. So this is C2. Here what they have said is initially S1 and S3 are closed and S2 is open, right? So how will my circuit be? There will be two independent circuit, right? Which is not connected to each other. This is V2, this is V1, C1, C2. What is the voltage across C1 initially?
0.
Voltage, yeah. What is the voltage across C2 initially?
0.
0.
0. After a very long time, what is the voltage across C1 after a very long time?
It's equal to V1.
V1. In the same way, the voltage across VC2 after a very long time is V2, right? Now, S1 and S3, I am opening it and only S2 I am closing it. Okay. So, my circuit will become like this. C1, C2. Now, what is the capacitance stored here at initial point? After connecting it, V1 is the voltage here, whereas V2 is the voltage here. So what is the like initially, what is Q1?
C1 V1.
Whereas Q2
And
is equal to C2 V2,
C2 V2.
right? And final, like after a very long time, it will reach such a way that both the capacitor will carry the same voltage, right? So
Yes,
Q1
ma'am.
will become C1 VF and Q2 will become C2 VF. Now, by law of conservation of charge, C1 V1 plus C2 V2 is equal to C1 VF plus C2 VF. So VF will become
C1 V1
C1
plus C2
V1 plus
V2
C2
all
V2
divided
by
by C1
C1 plus
plus
C2.
C2.
So
Yes,
like
ma'am.
this, we'll be able to find the voltage, right?
Yes, ma'am.
Yeah. So yeah, it's
Ma'am,
already
in
time.
this circuit,
Mm.
we don't have any voltage source. So the C1 and C2, they store their charges, right?
Yeah. So this is like, it's not like there are any source. The C1 and C2 are charged capacitance. So there is some charge present in the capacitor, which is powering up the circuit, right?
Yes, ma'am.
Yeah. And in next class, we will see problems related to this. Do you guys have any doubt here?
No, ma'am.
No,
Yeah.
ma'am.
Okay.
One
Then we
question
will
is that
stop.
what's the use of this time quantization and the amplitude quantization?
So yeah, see. The real-time signal, right? So it will be varying with time. And there will be infinite points in that time signal, in analog signals. But our computer will not be able to read infinite number of signals. It will be able to read only zeros and ones. Okay. So what we will do is first we will convert this infinite values into some kind of integers, as I said here. So yeah, here. So this is a real-time analog signal. Here, if you measure a value at 1 second, you will get a value. If you measure the same signal at 1.01 second, there also you'll get a value. Whereas if you measure it at 1.001 second, also you'll get a value. That's the characteristics of an analog signal. But um, so if you see it, if you will find a point for everything, there will be value. So there are actually infinite values in the time scale. In the same way, for a value at time t, the v of t will be like not 1.78. It will not be rounded off to two decimals. It will be like an 1.7823 into like some infinite value. The decimal point will be infinite term. So all these values cannot be read by a computer. So first what I'm doing is I'm converting all these values into some whole numbers. Then this whole numbers I can convert it into zeros and ones because our computers can read only zeros and ones, right? So that's why we are going to break down the time axis into some discrete values, breaking the y-axis into some discrete values, and then converting these discrete values into binary values. Then that binary values will be read by the computer. Is it clear? I hope it's clear.
Yes, ma'am, it's clear now. Thank
Yeah.
you, ma'am.
Yeah, thank you. So we'll end today's session. Thank you, guys.